Firstly, we'll be dropping the two mass at one height, which will result in one velocity, and we'll see what compression we get. From the footage, we can see we're getting a compression, 2 being 0 mark, we're getting roughly around 21mm. So that's the two mass dropping 1 unit of height, so 1 velocity. We're now going to drop the one mass from 2 heights, so it's not going to achieve twice the velocity, it's going to achieve 1.41, which would be 14.14. And in terms of momentum, obviously the two mass would have the higher momentum, but in terms of energy, these two will be equal. Obviously I measured the difference in compressions for the standing weights. It was around about 1 mil, so 1 mil off that, we'll be looking around 20 mil of compression for the one mass at twice the height. So from the footage we can obviously see that roughly we're getting that amount of compression for the one mass at 1.414 the velocity. That's at 2 heights, so the energies are the same. Momentum's obviously different, but the energy formulas predict the results. Now, when we look at this is inverse to the whole problem of launching a two mass with a set amount of spring and a one mass with the same set amount of spring. So what we've just shown there is that the two mass coming in compresses the spring. Given the same energy, the one mass also compresses the spring the same amount, but this is going 1 velocity and this is going 1.414 the velocity. So if we were to lock those springs off at those compressions, which is obviously equal compressions because they're the same energy, and we were to launch those masses, if this is coming in at 1 velocity and this is coming in at 1.41 the velocity, I think it'd be pretty ludicrous to think that by launching this mass, this one mass, with the same spring energy, that it would somehow then achieve twice the velocity, because we'd have to give it 4 times the energy. We'd have to go twice as high again for it to achieve twice the velocity. So we've got the same spring energy launching a 2 mass and then a 1 mass, or a 1 mass and a half mass, however you want to say it, but just by halving the mass alone with the same energy input, it's not going to achieve twice the velocity. This proves it. You know, it's just the inverse. I mean, you can make the argument that, you know, doubling the force doubles the momentum or the velocity, whatever, but that isn't your argument. Your argument here is, if we take a 2 mass and we halve that mass with the same energy, so we're not doubling any energy here, we've got the same energy input. So just by halving the mass doesn't achieve twice the velocity. And if you were to believe that, you know, this could come in, compress the spring at that speed, and then you could then lock that spring off, put that same mass on, and it would somehow magically come up with some free energy to go twice as fast. You know, it's just a ridiculous idea. You know, it's ludicrous, and this proves it. And like I say, we will drop the 1 mass from 4 heights, giving it twice the energy, allowing it to achieve twice the velocity. So that's coming up next. So now when we drop the 1 mass from 4 heights, it will achieve twice the velocity. And then pitching that against the 2 mass at 1 velocity, obviously they would be the same momentum, but we've had to put more energy into the system for that to happen. And according to MGH and kinetic energy, it is twice the energy. So it won't compress the spring twice as much. It should roughly compress it 1.41 times as much, so we'd have to calculate that. So obviously we can see from the previous 2 runs, clearly with this being the same now, the same momentum, in the previous test, because of the same energy, we got equal compressions there. So we're clearly not going to get equal compressions here, because now we put more energy in, it's going twice as fast. So for both of these cases, it was roughly about the 20 mil mark. 20 times 1.4 is 28 mil. So when we drop the 1 mass from 4 heights, now achieving the 2 velocity, in terms of energy and the energy equations, it should roughly compress the spring around about 28 mil. So again, we'll run that test, we'll show the footage, but point being is, here, if momentum was a measure of energy, they would be equal. We've already shown from the first 2 runs that that's not the case, so clearly momentum is not a measure of energy. As we can see from the final run, the 1 mass at 4 height, roughly in line with kinetic energy, MGH, the energy formulas, compressor spring, about 28 mil. So clearly, you know, the argument's over. So obviously MGH works, we've just shown that. We've got MGH on both sides of the equation, so we've got gravity on both sides, so we can just deal with the mass and the height. So we've got a 2 mass from 1 height, 2 times 1 is 2, and 1 times 2 is 2. So they are equal. Much the same as I previously showed, where I dropped a 4 mass from 1 height. So 4 times 1, 4. and 1 times 4, you know, so they're equal. So dropping a 4 mass from 1 height and a 1 mass from 4 heights is the same energy. I've already shown you that. Obviously you didn't believe it, you didn't want to accept it, but I've gone a bit more in depth with this one. Same results, because that's how nature behaves. And there you go.